Things started. Welcome. Another exciting week. Lecture 4. Today we're going to be covering moments, couples, and equivalent loads. Before we get started, does anybody have any questions from Zoom? All right, let's get into it. I got some good stuff for us later on. Made some changes. Hopefully they're improvements. But I started researching some other more costly solutions, so might have some better camera angles in the future. Need to figure out how to get up and over my monitor and top down all strong like, so stay tuned for that.
Mr. Rodriguez, can you hear me?
I got you, Dalton. What's up?
Oh, hi. So I was just clarifying the quiz, the second attempt, that's going to be tomorrow at midnight?
Yes. After this class, I'm going to go through both sections and paste the due date that I see into the due
Okay.
date in the details pane, so you can have that. I don't understand why it doesn't show everyone the due date and the close date, because it shows it for us.
Yeah.
I don't understand why Canvas is being like that.
Okay, yeah. And I saw the screenshot. I just wanted to clarify, I'm going to do it today anyways, but I just want to make sure just in case.
Yeah, okay. Late homework. We haven't talked about late homework. Talk to Emily about it, and I'll let her be the guiding force on that. Any other question before we get started? I had orange juice yesterday for breakfast. Ooh, it didn't mesh well with teaching online like this. Well, enjoy that VIP badge, Septic Kid. Okay, we've got nothing else. We'll hop into it. As I said before, we're going to be going over moments and couples, talking about equivalent loads today. Going back to quiz 1, it's been graded in both sections, the first attempt. Okay. If you scored above an 80, you have mastered the core concepts being taught in the lecture, namely position vectors, magnitudes, lambda, the directional unit vector, Newton's second law, and solving the equations. You've mastered those. I'm okay with you moving on. And we have talked internally about just not issuing you guys 80, 85, 90, whatever percent of the grade. Pass the quiz, you get 100%. Didn't pass the quiz, you got to go to the makeup, and you got to move on. You got to pass this first quiz. We need you to know these concepts before you move on. If you scored less than 80%, there's room for conceptual improvement. Review lecture examples in quiz 1 to answer to assure the completion of quiz 1 makeup. We need you to pass these. Yeah, that's okay. Quiz 1 makeup has a 2-day open period. Dalton just asked me about this. I'm going to post the due date so that you guys can see this, so that you don't stress out, because I've got so many messages about when it's due, and I don't know why it's like that. It should just show you. Had something about quiz 1, but it evaded me. Anyways, we'll move on. Question about quiz 1?
Professor, I do again. I apologize.
Sure, absolutely. Go ahead.
So, thank you. I was looking with the attempt 1. It says that there's only the 2 questions. So are we not uploading our work again, or is it like under one question? It like has another part where you.
Quiz 1 makeup.
Yeah, the makeup.
Oh, quiz 1 makeup does not have the first giveaway problem. It doesn't have the 20.1. We just went with one question, all or nothing. Show me that you can do position vectors, the directional unit vector, setting up Newton's second law, and solving. Show me you can do those things.
That makes sense.
And then the
Perfect.
second question is the file upload. Yeah, everyone should pass this. This is not. I'm not trying to trick you. We know what to do. We have examples of exactly what to do in class. You should have 90 minutes for that too. Let me check that quiz 1 makeup has a 90-minute open period, but you got plenty of time. You can do this. These are not concepts that are difficult to master. Everyone has the skills to do this. We can all do this. Let me make. Thank you for confirming that, Dalton. Let me make a note of that, and I'll make sure. Actually, right now, like, reply to that email and press ping. Like, just write ping in there to make sure to remind me to go back and look at your grade for quiz 1. I'll take care of that. Oh. So Natalia was supposed to be responsible for quiz 1 and the grading, but her classes have been a little more than she anticipated, and so I was like, oh yeah, sure, I'll grade the quizzes. Man, that sucked up like 15 hours of my weekend. Quiz 1 ended for the first class Friday at midnight. I was like, you know what? I'll just stay up to midnight and I'll just grind through them. Everyone's asleep. The whole house is quiet. I could just grind through. 4.5 hours later of grading quiz 1 submissions. That was awesome. Made me feel good. All right, let's move on. Video of the day. We've got 24 participants in the Zoom chat. I don't know how many we have on Twitch. I don't keep that number open. Let's go check out the video submitted by Adam Badu. Pause the music for a second. Valhalen, what part of the engine are you talking about? Because not one person designs everything. Yeah, I thought that was pretty cool. So thank you so much, Adam. Appreciate that. Again, if you want to submit a video for us to watch in class, modules, and I think that Natalia made it an assignment, the worth 0 points, so you just submit a link there and check it out in class. Okay, let's get back into it. Propulsion. A lot of propulsion is done by chemists because at that efficiency, at that level, they want to make sure that every single particle of fuel is being mixed with the right amount of oxygen and being heated the right amount. And so that is a chemical reaction. If you want to talk about turbines, aerodynamicists are going to deal with that. Aerodynamicists are going to do a lot of the things, but propulsion is one of those things where you're like, are you talking about how we're compressing air or how the mixture is happening? Stoichiometric. Yeah, it has to, well, supposed to be perfect. All right, so let's move on. Dalton, submit it. Okay, so today's learning outcomes are going to be to apply the principle of transmissibility to move forces along their line of action, and to compute the moment generated by a force with respect to any point in the system. 2D, I didn't get to 3D yesterday, but I'm going to try to stick around after this lecture and create a video. I didn't get to it yesterday. Hungry and all these other human factor things, but today I want to get this done so that we have a moment generated by a force in 3D. We have that example. Okay, so let's talk about equivalent forces. And the first one we're going to use is something that makes it easy for us to make calculations later on. So we're going to talk about this, and it's called the principle of transmissibility. States the conditions of equilibrium motion of a rigid body will remain unchanged by a force F if acting at a given point on the rigid body is replaced by another force F prime of the same magnitude and direction but acting at a different point, provided that the two forces have the same line of action. I'll let you guys read this, absorb it, as this is something that we're going to use and abuse to make our math easier. Move on. Equivalent forces. The principle of transmissibility is only applicable to external forces. It is not used to find internal forces. And this is the class we went through, the internal external exercise. So the external of the hand is something we can find. The internal of the hinge on the pin, something we cannot find using the principle of transmissibility. So truck here has a weight, 2 reactionary forces on the wheels, and it's got 4 people pulling on a rope in front of it, F. If you take those 4 people, exchange the rope for just their hands and push on the back of the vehicle, same thing, it's fine. Okay, moving on. All right, think about this for a second, and I want to see yeses or nos in the chat. Is this true? Anybody for yes? I didn't get anybody with this today. This is like one of the very few times where I'll give you an I gotcha question. Wilbur, I'll go yes. Yeah, Wilbur, if you can unmute and describe why you think it's yes, we'll hear what kind of possible answers we can have.
I just want. Shit.
Explain to us why it's no then, Wilbur. Sorry, no mic right now. All right, Ryan Murphy.
Was that?
Ryan, explain to us why it's no.
Because in the first, so on the left side of the equation, it's a pulling force, just so it's just horizontal. But when you have that, in the right side, it's a top. The force is high up, so it's pushing it around the center of gravity of the truck. So it's creating like a rotational force instead of just a straight. Well, it's both rotational forces, but they're in different directions. If that makes sense.
Yes. Not quite what I was looking for, but yes, this is not true. Anybody else want to take a stab at this? Rashad?
I was just gonna say it's not on the same line of action. It's raised.
Correct, and that's really the big deal that we're dealing with here. So if I go back a couple slides, this says same magnitude and direction, which is something that we satisfied with that. F and F prime looked the same magnitude and direction, but they are not acting on the same line of action. So it was Ryan that what happened here? So we talked about rotational, what the truck would actually feel, and he's spot on with that, because on the left hand side, if you put a pin at W and we're able to pull F, it would rotate counterclockwise. Is this counterclockwise to you guys? It's counterclockwise to me. It'll rotate counterclockwise. But if you put a pin at W on the picture on the right hand side and push with F, the truck would rotate clockwise. Ryan, it's okay. As long as you're brave enough to speak up, I don't care. But we like to hear these dissenting arguments, because you're going to be in a boardroom one day and people are going to say, no, that's not right, and have some physics or math to back it up. And you just have to be able to keep your wits about you and say, no, like, we go back to first principles. These are why we cannot do that, or this is why we can do that. So we're all good here. So correct answer was no. Even though it's acting in the same magnitude, same direction, it's not on the same line of action, and therefore this is not true. Cannot do this. Okay, talk a little bit about vectors and in of plane and out of plane graphical representation. Okay, we've talked about this before, where the overhead arrow notates a vector. Boldface font on the computer, obviously. So the properties are going to be the direction has an orientation of the segment and the sense of an arrowhead. Magnitude of vector v going to be the double line, and the single line going to be the length of the segment. So I made this mistake earlier. Moving forward, I'm going to be using double absolute values for the magnitude of vector v and single absolute values for the length of the segment. So, for example, like cable TAC, that length will be denoted with single absolute values. And examples of vector quantities are going to be position, velocity, acceleration, momentum, force, and a moment. Pretty familiar with those. We're also going to introduce a zero vector. Zero with a arrow over the top of it has zero magnitude. Not super important right now, but later on we might use it for mathematical purposes, so keep that in mind. Oh, and then at the top we have out of the plane and into the plane. Figured out I can move that. So these two are based on the right-hand rule. So if we were all in class and COVID wasn't happening, I would teach you that your thumb is going to be your segment vector. So whatever your resultant vector v is going to be of the coming steps, your hand is going to tell you what direction the rotation is going to be. So your resultant vector is going to be pointing towards you. If it's pointing out of the plane, then we're going to wrap our fingers this direction, and it's going to tell us that our rotation is going to be in the counterclockwise direction. If the resultant vector is into the plane and we have the rotation, our finger is going to tell us that it's going to be a clockwise rotation into the plane vector. Thought magnitude was length. We solve for it like that, but in order to be specific with math, we're going to use the length of the segment as a single absolute value, and magnitude being its force, double absolute value. Stephanie. Yeah, this is my fault. I should have been this. Notation is huge, right? And many of you guys are in Professor Hunter's class as well. Notation in her class is huge. So I want to make sure that I'm consistent in this class, so that you don't get conflicting messages and have professors that do things differently. I just want to keep it all the same. And we're all using Paul Midige's notation. Okay. We happy with this? We okay with the right hand rule? Because if you do this with your left and you're like writing with your right, this is it's not gonna work. It's gonna come out backwards. Dalton, hit me up on Discord. We'll get you through this, brother. All right. Next slide. Vector products. So our vector product v, vector v, is going to be equal to P cross Q. And in the top right, we have vector P, we have vector Q, and similar to what we were doing before, with X is in the index finger direction, Y is in the middle finger direction, and orthogonally, your thumb is in the K direction. You can relax these two fingers and say that anywhere less than 90 is the same type of thing, and kind of keep them in the same direction. So P, I point in the direction of Q, and my resultant vector is going to be vertical out of the page according to picture A. And picture B, I mean, shows that that's what it is, but kind of not a very good drawing. Its magnitude can be found by multiplying P times Q times the sine of the angle between them. In this case, it's named theta. Okay, the vector product direction is going to be perpendicular to the plane containing P and Q. So the plane here, P and Q, the resultant vector of this cross product is going to be out of that plane. It's going to be perpendicular to it. And its positive direction is based on the right-hand rule. This one is going to trip up many of you, and it's you just have to wrestle with it. It's fine. It'll take some time, and the more problems you grind through, the more mistakes you make, the more you'll be like, no, like I got this. See so many people in class going like this and looking at their fingers and rotating, and super interesting. But you guys don't have to have that embarrassment. You all do it at home. It's fine. Physics gang sign. In mechanics, vector products can be used to describe rotations. That's what we are going to be using them for. And when two vectors have the same direction or opposite directions, their vector product is 0. This one's kind of important. Think about this. If your vector is pointing in the same direction and you cross them, there is no product. They're in the same direction. And so physically, if you have two vectors in the same direction, it's going to just accelerate that direction. It's an unbalanced force, and so it'll accelerate, and therefore not part of this class. That'll be an F equals ma equation. If the two vectors are in opposite directions, you have similar problems. Either the vectors are equal in magnitude and they cancel each other out, and it is this class, but it will not result a rotation or resultant vector out of the page. It'll be equal to 0. Done. If the magnitudes in opposite directions are not equal, if you add them together, there'll be an acceleration, and therefore not part of this class. And F equals ma is the equation we're going to be used there. Okay. Picture on the right is another example of I cross J is going to equal K. We'll get to this more in just a second. This picture is kind of interesting. This one is a little more complete than I would write it. I'll write this on my paper and kind of show you the shorthand way that I do it. But essentially, you write X, Y, and Z, and these are written in an n vector. An n basis vector is what we call the Newtonian frame, and that's supposed to be stationary on Earth. It's kind of your ultimate reference point. It stays put. This could be B, it could be C, it could be any letter you want that shows a different basis vector. In this particular example, it's called n. Irrelevant. Additionally, we have X, Y, and Z here in a triangle. And I will write X, Y, and Z in a triangle. And if you cross X with Y, say you're going counterclockwise, you're going to use these words. Unit vector product read in this direction are positive. So if you have X cross Y, the resultant vector will be in the Z hat direction, and it will be positive. That's what this little line leading to inside circle is. If you have Z cross Y, then you are traveling clockwise, and that's when this is true. Unit vector products read in this direction are negative. So you will do Z cross Y. Whatever math comes out, you'll stick in parentheses. And then, just like we did by inspection, you'll put a negative because I inspected that I'm Z cross Y and it equals X. And so I'll put an extra negative on the outside of that equation. We'll come back to this. This is another one of those things that we'll all draw on our papers, and we might make mistakes here and there, but it's pretty simple. Got to wrestle with a little bit. Let's move on. Moment of a force about a point. The moment of F about O or not. Well, O or not. Not is generally the more accepted term for the 0. The moment F about point naught is defined as the vector product of the force's position vector and itself. The equation for this is going to be the moment about point naught is equal to the position vector of P relative to naught cross vector P. So R cross F. Distance, moment arm, across the force being applied. This is important because mathematically this is not communicable. Ooh, I got it. has to be R cross F. It has to be distance cross force. Okay, and this measures the tendency of a force F to make the rigid body rotate about a fixed axis directed along m naught. This whole moment about a force measures the tendency of the force F to make a rigid body rotate. So if this rigid body is the one in question, if we did R cross F, we're measuring what this force F forces this body to rotate about point naught. Okay, and since we have R cross F, and we've all done cross products before, the tendency to rotate depends on the magnitude of the force. The tendency to rotate depends on the magnitude of the force and how far from the pivot point the force is applied. We have a graphical representation here of the position vector, OP. So if we increase the size of OP, the length of OP, then R increases. And if we increase the force being applied, F goes up and therefore m naught goes up. So it makes sense, right? The longer moment arm you have, the bigger the moment. The bigger the force you have, the bigger the moment. So if either one of these goes up, the moment goes up. Any questions on this one? Long enough stick and you can move the world? Technically, the world would move the stick and you just drift apart. All right, any questions? Moving on. Let's do an example. Okay. A 20-pound force is applied to the control rod AB as shown. I'm going to be calling these member AB and because this is actually a rigid body member. So when you see something like that looks like AB, calling it a member is a little more a little easier for someone else's mind to pick up and know exactly what you're talking about. An Archimedes quote. Dope. Did not know that. So, knowing that the length of the rod is 9 inches and that alpha is equal 25, determine the moment of the force about point B. Do this two ways. We're going to resolve the force into horizontal and vertical components exactly as it sits. The typical y is up and x is out to the right. And then we're going to do it again by resolving the force into components along AB and in a direction perpendicular to AB. That's fancy for saying we're going to rotate the coordinate axis, and we're going to use the principle of transmissibility to simplify our math equations. Any questions on this? Let's get our pencils, piece of paper out. Draw your free body diagrams, copy things down, start the example with me. I'm excited. I'm going to show you guys something new pretty soon. All right. New reveal. We got better. We got a different camera angle. Hopefully it's gonna be better. Fills up more of the screen, but the only challenge I have with this is like whenever I move anything on the desk, the camera shakes. But I'm trying. Okay. Does your free body diagram look like mine? Okay. So I have my drawing redrawn here. People always ask me like, why do you redraw these? And yeah, it's for you. Even when I was going through school and taking this class, I would redraw the picture simply because if you're staring at a blank piece of paper and you don't know where to start, redrawing the picture, it allows you time to like do something else with your eyes in your hand because you're just like copying, right? You're not really thinking about what you're doing. And it allows your brain to kind of process what's actually going on here. Where's this angle measured from? Where's this force being applied? What are these vectors asking for? Like you have time to kind of think about it and process. Like when someone asks you an interview question, like, well, tell me about yourself. And you're like, that's a really good question. And then you start. That's a really good question is one of those stalling tactics that your brain can use so that you can like load into RAM your thoughts that are going to come and it comes out nice and smooth. No stutter. Facts. Okay. So that's a reason why I like to go through these. Kind of gets me primed up, familiar with the problem. And then I don't need to keep looking back at my reference source. I can look at my drawing. Okay, so I have my free body diagram at A. And let's turn this on. Yeah. Oh, I made this bigger too. Although my head blocks a little bit of it, you still see most of it. Okay. So, have my free body diagram. And I want to resolve the force components. Resolve the force into horizontal and vertical components. So, I have a standard Cartesian coordinate system. X off to the right. Y going vertical as I see it. So we want to answer the question, and the question is saying determine the moment of the force about point B. So I'm looking for vector M about point B equal. Okay, and if we go back to what M is equal to, it's gonna be here. R cross F. So let's find the R vector, then let's resolve the F vector, and compute R moment. Oh, Dalton, you're absolutely right. My drawing is missing the length. Keyboard's in the way now. Good catch, Dalton. And we are at 9 inches. Okay. Good. Now I think that we are set up and ready to go. The R vector. So, step 2. Define R A to B and force in X, Y hat. Okay, so let's start with our position vector. B relative to A. And this is also going to equal vector BA. This notation was a little bit tough for me to get my head around, why you write them in this particular order. Professor Hunter probably has a much better explanation for why we do that. I like to get it into a form that I enjoy, which is BA.
It's quite hard to look at the fraction part of it though, like the A fraction sine B.
Oh, is it hard to see it? Is that what you're saying?
Yeah, yeah.
Yeah,
Just to make it clear.
that's why I'm gonna go BA here. Because I've tried like writing bigger, and it makes my handwriting looks terrible. And yeah, that is Trevor. That is 9 in this font. Says she doesn't like to use a fraction notation. Okay. Cool. Well, I will write it down, and then I will immediately switch it into this notation so that we can see it, and I enjoy it better. Okay. And so the position vector is going to be... We're going to look at this drawing for it. Length B. And we're going to be using this interior angle beta, 65 degrees. And so if I want the x direction, I'm going to be using the cosine of this, since I would like this length here. B, why is it B? It's L times the cosine of beta, x hat direction. And by visual inspection, x is going to the right. My length is actually going to the left, so I will put in a negative sign. And that takes care of the x term. And we will add to that L times the sine of beta in the y hat direction. Y is going vertical. Our membrane BA is going vertical, so that will remain positive. And we have our first component of our moment. Yeah, if we haven't figured out now that Zoom is messing up the quality, I don't know. I stayed online yesterday with Sean Myers, and I tried to fix it, and I broke everything. So I'm trying. Try to get the Zoom quality up higher, but right now, go to Twitch. The VODs are saved there. I've downloaded the VODs. I'm going to make a YouTube channel for you guys to have these indefinitely. Let's define the F vector. Okay, so now I go to this picture, and now I'm looking for the x direction. So I'm going to multiply f times the cosine of alpha in the x hat direction. F is going to the right, x is going to the right. This quantity will remain positive. I'll add to this f sine of alpha, y hat direction, and by visual inspection, vector goes down, y is going up, we'll add a negative sign. Yeah, Ryan, I think it's Zoom's fault too. They're doing something with the transcoding, because I can get high quality stuff here. Really? Yeah, she's in there. I think so. Nope, not there. Okay. The joys of broadcasting from your bedroom. My niece came in. Okay. Yeah, I put a B in there. That does. I copied over the B. It should be the length L. If I had an eraser, I would erase it, but I don't. Oh, I should get. Write that down. Whiteout. Thank you for that. Thank you for that. Okay. So now we have our vector, we have our moment arm, and we have our force. So now let's carry on the calculation of compute moment about point B. So we'll go back to this slide. Moment about point B is equal to R cross F. R is going to be negative L cosine beta x hat plus L sine beta y hat. We're going to cross that with F cosine of alpha in the x hat direction plus negative F sine alpha in the y hat direction. We happy? We tracking? Okay. So now we go back to this slide. And we see when two vectors have the same direction or opposite directions, their vector product is 0. Same direction is the word we want to concentrate here because same direction means x hat, y hat, z hat. If two vectors have the same x hat, y hat, or z hat, their product is 0. He literally tucked himself into the bed and he's barking from underneath the bed right now. Navas? Nope. Wasn't the dog. It was grandma telling me she's leaving. He's in the bed right now. Tucked himself in. Unmade my bed. Where were we? So we're about to FOIL this R cross F. X cross X is going to be equal to 0. Y cross Y is going to be equal to 0. So let's FOIL this out. Where negative L cosine of beta times F cosine of alpha in the x hat direction is going to equal 0. We'll move on to, let's write that out. Negative L cosine of beta times F cosine of alpha. And I'm going to cross this out, and I'm going to call it 0. Because x cross x is equal to 0. Move on to L sine of beta times F cosine of alpha. Okay. So now I have a y cross x. The resultant vector is probably going to be z because I don't have a z, but what direction? So this is when I write out x, y, and z. Okay, I don't care what direction you put these, where you put them. Z's on the top, Y's on the bottom. That doesn't matter. What you need to think about in your head is that with the right hand rule, x cross y equals z. That's the right hand rule. So x to y is going to equal positive z. So I'll start at x, and I'll go to y, and I'll put a positive there. There are so many different ways you can draw this little drawing to prove it to yourself. This is just the way I do it. I don't care how you do it. Are we tracking with this little drawing? This is how I simplified it from the other double one. Something happened to music. F's or pogs in the chat. I need something here. Thanks, Jose. F on the drawing. We'll do it many times. We'll do it many times. But X, Y, and Z, from X to Y, arrow, make that positive. Alpha? I don't know what that means. I'll go through this because I'm getting a lot of F's. It's okay. All right. So Y cross X is going against the positive direction. So I'm going to add a negative in here. And I didn't leave enough space, so there's an extra negative hanging out in the middle of space. And that is going to be in the Z hat direction. So I did X cross X and Y cross X. Then I'm going to do X cross Y. Negative L cosine of beta multiplied by negative F sine of alpha. And it's X cross Y. X cross Y is going in the positive direction, so that will remain positive. And the last one is L sine beta Y hat times negative F sine alpha Y hat. These are also going to equal 0, because Y cross Y is equal to 0. Ah, yes. I'm using sine. Sine is just a capital S, subscript alpha. Thank you, Ryan. Appreciate that. Okay, so like I did here, I'm going to write them out. Negative F sine of alpha. And all of this is going to equal 0. Because Y cross Y. And this one is X cross X equal to 0. When I upload a high resolution copy of this, you'll see the little notes that I made. But generally, you don't need to write these out. You could just skip over them and only be left with two components. Okay, so let's compute. This is going to be negative 9 for the length, inches, sine of beta, which is 65, multiplied by F, which is 20, cosine of alpha, so I have negative 9 inches, sine of 65, multiplied by 20 pounds, cosine of 25. Just filling in the knowns, our variables. And we're going to add to that negative 9 cosine of 65 times negative 20 pounds, inches, sine of 25. And I know that I do this on my paper, but I do this to keep everything on one page. If you're submitting homework or quizzes, just go to the next page. It's fine. Don't do as I say, not as I do. I just want to keep everything here so that it's consistent for you guys on one page. Don't do this on your homework. Oop, that's not a 4. Moment B. I don't know where I put my calculator. Found it. Can we see this? That's pretty good. Okay. Negative, parentheses, negative 9, sine 65, close parentheses, times 20 cosine 25, close parentheses, enter. Negative 147. Check the notes. We good. And the units on this are going to be inch pounds. Open parentheses, negative 9 cosine 65, close parentheses, times negative 20 sine 65, close parentheses, enter. 68, did we get that right? We did not do that right. What happened here? 25. So I made a calculation mistake here, where on my paper I wrote sine of 25. And in my calculation, I wrote out sine of 65. These errors are super minimal, and as long as you show your work and what goes into it, if I would have put the 68 here, I'd have gotten most of the points. Maybe 2 or 5 points off, depending on the value of it, but it's going to be super minuscule. Don't worry about calculating things incorrectly. My favorite part about vectors is little hats. Hey, I like those. Okay, so those added together will be MB equal to negative 115 inch pounds. The negative is important for us right now. Anybody want to be brave enough to talk about what the negative actually means in this example? Oh, somebody was unmuted. They're like, I want to be brave enough.
Is it that it's going into the page?
Yes, going into the page. So let's unpack this a little bit. The negative 115 means that based on our coordinate system, if x is this direction, y is this direction, the positive moment will be notated like this little picture that I drew before. Positive, positive, and that's my moment, positive direction. That's the right-hand rule. Because it's negative, it is not acting in this direction, so I can report my answer as 115 inch pounds, and I can draw the vector the correct direction. Or I can put clockwise, CW. So this would be generally the most accepted answer. Negative 115 would be fine too. You could circle that. Not a big deal. But in your head, you should say, okay, if it's acting counterclock or clockwise, does my picture agree with that? And so if I'm looking at point B and I have a force vector that's pushing this direction, pulling this direction, the tendency for it to rotate is around B in the clockwise direction. Should we include the z-hat in our answer? No, you should not, because this is actually the rotation. You're reporting... I can go back to it. I don't have a good example for this. So this is what we are using this for. In mechanics, vector products can be used to describe rotations. We are describing rotations with these moments. So when we want to describe the rotation, simply putting clockwise or negative 115 pounds. I guess the negative 115 pounds, you could put z-hat here, showing that we rotate about this point. But that's still, no, that's not true. You can't do that. Because a moment is not in that axis. Okay. we would expect that since the force would make the arm rotate clockwise, right? Yeah, we would expect that. By visual inspection, you know, if you set this up and you pull the string, it would rotate clockwise about point B. Okay. We happy with this? Let's move on to part B. And remember, point B, part B, is going to be resolve the force into components that are along AB and in a direction perpendicular to AB. No, Ryan, it cannot. Because once we do the X and Y calculations, actually, that's a more complicated question, and I don't know what you're looking for, but we'll talk about the different ways it can be reported. Because if we're in 3D, we can have a rotation about we can have a rotation about axis Z, we can have a rotation about axis X, and we can have a rotation about axis Y. It can't because it's a cross product, but if you have multiple things working on a particular body, you can have rotations about all three axes. So we can report a force in the X, a force in the Y, a force in the Z, and we can report moments about X, moments about Y, and moments about point Z. Axis Z. Force about points, moments about axes, because they're rotations. Okay. Let's move on. And we're in lecture 4. Example 1. Part A. Okay, and I'm going to draw the same thing a little less neat this time, and we're going to see what it's like if we have a rotated coordinate system, what it does to our calculations. Okay. Again. Member AB. And so B, A, okay, and again our knowns. Length is equal to 9 inches still. F is still equal to 20 pounds. Alpha is still equal to 25 degrees. Beta is still equal to 65 degrees. I think that's all I need. Okay, again, so we start with our free body diagram at A. Okay, so now in the free body diagram, we would like to resolve the force into components along the B and in a direction perpendicular to AB. Which means in this picture, I'm going to show a rotated coordinate system axis, which this will now be Y, and this will now be X. We tracking with this? So I'm going to introduce a new angle. It's going to be tough to see, called gamma. And gamma is going to be equal to, since we know that alpha is 25, and beta is 65, I can use interior angles to know that this total distance from the horizontal to member AB is going to be 65. So I can do beta minus alpha. Is this the way it was done in the example in the book? I'm not sure, Rashad. I'm not sure. It probably is. I know there's a question on the homework very similar to this, so pro tip, if you're doing the homework, this is on there. Are we happy with gamma equals beta minus alpha? Using alternating interior angles and beta. And so that's going to equal 40 degrees. Perfect. That's why I asked. Okay. So we're all set up now. We have alpha defined. We have gamma defined. Let's move on to resolving. I can't move the paper. Ooh, I want to draw over here. So it is moment is equal to r cross f. So let's draw r first. Resolve BA and F in X and Y. Okay, so member BA in the rotated coordinate system axis, distance from B to A is still 9 inches. And it's going to be in the X direction, so BA is equal to 9 inches. Oh, I should not do that. L. I cross this out. L, X hat. And since it's going from B to A, and I have X set up going downward and to the right towards B, this is going to be a negative length. Gamma is smashed in between this little spot here. What happens when I don't use a ruler and stuff. So gamma is the distance between gamma's right here. I put gamma here, but it's a pretty bad drawing. Okay, we all happy with how we have negative the length in the X direction based on our rotating coordinate system? F's or pogs in the chat. We got to get some type of feedback here. Okay, and then we'll add to it the Y direction. And since we have our Y direction, big F, this is why we got to wrestle with these problems. We just need a little bit of time with them. Because it's not a difficult concept. We just need to pay attention and be meticulous. And in the Y direction, we don't have any. We have no direction in the Y hat direction. Okay. Why is X negative, and why do we have Y? Okay, so I have now taken my coordinate system from the standard X and Y, and I have rotated it to be along the member AB. So if this is member AB, this green pen is member AB, this is Y and this is X. From B to A, from point B to point A, that distance is 9 inches. It's L. We have defined from the cap to the tip to be positive, that direction, downward and to the right. From B to A, that is going the opposite direction. So from B to A, it looks like it's going negative L inches. Tracking, Wilbur? So that's why it is negative L in the x-hat direction. Okay. This is another thing that tripped people up on the quiz. Relative to one point relative to another point, and what makes things negative. So I'm okay with answering these questions. And then 0 y hat, because we have we have nothing in the y. It is essentially on the x-axis, so we don't have a y component. So if we rotate our coordinate system, we only have one component taking part in this moment calculation. Okay, so let's go on to F. F in the x direction is going to be equal to F cosine of gamma, x hat direction. We've defined it down to the right. F is going down to the right, so it's going to remain positive. Y hat direction is going to be magnitude F times the sine of gamma. And y is up. F is also going up, so that value will also remain positive. And are we happy with how we got here? Okay. Let's set up our moment calculation. Compute moment about point B. So moment about point B is going to equal BA cross F. Moment about point B is going to be negative L x hat cross F cosine of gamma x hat plus F sine of gamma y hat. So for the moment calculations, I really enjoy the use of brackets here to separate the two values so that I know when I'm adding and when I'm multiplying. Let's plug in the values. Moment about point B. Actually, no, let's do the calculation and then I'll plug in the value. So negative L x hat times x hat. We don't need to do that calculation. We know it's going to be 0. I'm not going to copy it down again. Fine. So I'm going to do x cross y. So negative L times F sine of gamma. And I'm doing x cross y. Let's redo that picture. And I'm going to do it much bigger this time because I have a bunch of space over here. So x. And let's just say I put y over here and z over here. And I'll do it again where we have y, x, z, and then x, y, z. So all three vectors there. So you can draw either one of these, any one of these three pictures. Okay. So I know that via the right-hand rule and this motion that I do in class all the time, that x cross y is going to be positive. I know that. I know that x cross y is positive. I know that. And x cross y is positive. Do we understand this picture now? What this thing does? You can draw it any way you'd like. But I start at x, I draw an arrow to y, and then I put a positive there. So no matter how you do it, the right-hand rule x cross y equals positive. And that's like your standard right-hand rule. Okay, so I have an x cross y, which means this value will remain positive, and I don't put an extra negative. And so this will equal negative 9 times 20 sine of 40. Somebody's burning something around here. Negative 9 times 20 sine of 40. Negative 115.7. What do you know? I might round this up to negative 116. So MB. Actually, what did my last one come out to be? Oh, I didn't do it. Okay, so they literally came out to the exact same thing. 115.7. I probably should have rounded that up to negative 116. It's still within the margin of error. It's fine. Somebody want to enter? Oh, I totally did. Totally did. Somebody want to answer Deshant in the chat? In the Zoom chat? Okay. So, negative 9 times 20 pounds sine of 40. Negative 115.7. And again, this answer is negative because it is not going the direction that we set forth here. It is going in the clockwise direction. 115.7 inch-pounds in this direction. Or clockwise. Is it blurry on Twitch too? Thought I fixed this camera today. I'm doing the best I got, man. Doing the best I can. See. Yeah, it looks a little fuzzy up here. And it looks really clear right here. So that's probably a function of where I have the focus set. Yeah, look how clear that is there. Woo! Yeah. Okay. We'll talk about this one day. Because this camera is a DSLR on a tripod. This thing is super precariously placed tripod, and I actually have a backpack holding it down on the other side. So, what it do? Yeah, I wish I could show you guys. Actually, I will do that. I'm gonna take a picture of this because it's ridiculous. I'll post those in the Discord. Yeah, this is ridiculous. Can I do this? Is this a thing? No. Anyways, I'll post them to the Discord. You guys check it out. But, are we happy with this? And did you see how I use the principle of transmissibility to kind of backwards simplify my equations by getting rid of one component in the y direction and rotating the coordinate system. And I don't have a cosine and sine here. I only have a number. So that makes my calculation -9 times 20 cosine of sine of 40. Super simple calculation. Okay, so we've reached the point of the class where we got 15 minutes left. If you're in the Twitch chat, go ahead and leave the Twitch chat and join the Zoom call. I'm going to be ending the Twitch chat early, and we're going to talk privately inside of Zoom. So go ahead and do that now. Big Sad, it's fine. We're good. Gibbsy. I've never seen that emote before. Sneaky hey. So go ahead and close the Twitch chat. Join in the Zoom. Sneaky bye. Join the Zoom, join the Zoom, join the Zoom. Okay. So we go in here. Bye-bye. I'm cutting off the stream. Go to the Zoom. Go to the Zoom. Bye-bye.